A couple of comments on yesterday's handout and topics.
So go to slide 116, and well, I'll give you a chance to get there.
Slide 116, second line from the bottom.
So the parentheses after the p should be moved to after m squared, and the minus sign should be changed to a plus sign.
Then you don't have to change the minus sign.
Oh, okay.
So just move the parentheses.
All right. Oh, I'm sorry.
But you probably already spotted that, right? Last night when you went through this? Yeah.
So anyway, so that's one thing. And then one other general comment about yesterday that I have, just that I didn't actually mention in the morning, but everything that's relevant to regression, linear regression, outliers, Bonferroni corrections, multicollinearity, it's all relevant to what we talked about yesterday. So it was just linear regression generic, nothing special in Mplus. But we do also have outlier detection in Mplus, which we did not mention yesterday. There's an outlier option in the output command, and you can also save all of those outliers in the save data command, and you can read about the ones that are available in the user's guide. Okay?
And I wanted to mention one thing that we didn't have time to talk about. I think since you're doing latent variable modeling, and since the topic yesterday was structural equation modeling, I think you should join SEMnet. Here is the link for joining SEMnet. That's on the last page, 271 of yesterday. Very easy to join, and you can ask for a daily digest, for instance, like I do. I think SEMnet needs an infusion of new methodological strength that you have in the room here. It'd be good to have some of you participate in the discussions and share your experiences. I think that can enrich the field. And I also wanted to say that before I forget, there is a training session, another training session on Mplus beyond those that we provide, which will happen at the SPR, Society for Prevention Research. Society for Prevention Research has a meeting every year at the end of May, early June. And I believe the next one, this coming one, is in Washington, D.C. Does anybody know? San Francisco. Oh, yeah, that's right. Every other year on the other coast. So San Francisco next, or this year, this end of May, early June, there will be one-day pre-session using Mplus, one-day pre-session using Mplus on the topic of survival analysis, taught by my former student and professor at UC Davis, Catherine Mason, and Professor Hanno Petras. So we're going to put that on our website. We haven't put it up yet. So you have a possibility of getting a head start on survival analysis learning, which we will also talk about. We'll teach that topic in August here in this room. One more thing I wanted to tell you about. If you go back to slide 247, and we're still on topic 1 here on the right screen, I wanted to mention this for 2 reasons. One is that if you look at this model on slide 247, and if you ignore this idea of the interaction here, which is marked by these lines and that filled circle, if you just look at it as a standard linear structural equation model, This is a good example of a model that you can break down into testable subparts. It's an example where that works. You know, we looked at the weak net all model, and it doesn't quite work there because we have too few indicators. But here you have a situation where you could break it down. Let me tell you how I look at this model. I would not start with this model. I would never start with a big model like this. What I would do is, I would probably, if you want to put circles around parts of the model, I would probably circle this part, the exogenous part of the model, with its factors and indicators, as one measurement part of the model that I want to explore first and see that it tests well, that it fits the data well. With the idea that if any part of the model doesn't fit well, the whole model is not going to fit well, right? So any part, it's a necessary requirement that parts of the model fit well for the whole model to fit well. Certainly, there can be cases where the part doesn't fit, and that's obscured by testing the whole model. But that's like sweeping something under the carpet. You don't want to do that. And then another part would be this endogenous part. Either do it separately or together, as you will have to do here, since separately each of these has only 3 indicators and fits perfectly in a trivial way. And that's not a good thing that it fits perfectly with 3 indicators. You have robbed yourself of the possibility to reject your notions, your ideas. And you should always have the possibility of being contradicted, because as you know, you're probably always wrong. So probably always wrong, and therefore you want to be contradicted by data. So anyway, I would look at this part as a second measurement model part. And then I would look at the parts together, where you, at the first step, you would just take these 1, 2, 3, 4 factors as perfectly correlated. So in a factor analysis, in a CFA, you would put them to be perfectly correlated. That will introduce, although that says nothing about the structure among the latent variables, that will then introduce the cross covariances between these y's and see if the model fits well. You know, if the correlations between this set of observed variables and that set of observed variables go through these 4 factors. So that will test that. And only then, as a last step, would I add the further restriction by having this path model on the 4 factors. Because this path model is restricted by saying that there is no arrow from F2 to F4 and no arrow from F1 to F4. So it has 2 over-identifying restrictions, as the language is, beyond letting these 4 factors be freely correlated. So step 1, step 2, the whole measurement model in CFA, step 3, and step 4, the structural equation model. That's how I would go about it, and you would have a better chance of pinpointing where the misfit is. 2 more points on this. If you look at this part, you can look at that as, could be that F3 corresponds to a factor at time 1, and F4 corresponds to a factor at time 2. So Y7, 8, and 9 are the same items as 1, 10, 11, and 12. So you have what I would call a longitudinal factor analysis situation here for F3 and F4. And we get questions about that quite often. I don't know that we have an example in the user's guide on that.
Well, we do. We have the individual, or the multiple indicator growth without a growth model is the same thing.
Oh, that's right. So we have actually in the user's guide a multiple indicator growth model, so that we have a growth model that governs the development from F3 to F4. Growth model sitting down here below there. So the simpler case of that is just a longitudinal factor analysis model. And that's interesting related to yesterday, because we talked about measurement invariance testing and restrictions in the context of multiple group analysis. Here is a case where you would want to impose measurement invariance across time in this single group. So everything you learned yesterday about measurement invariance testing in the multiple group setting carries over to this single group to multiple time point setting, where you test the invariance of these measurement parameters, loadings and intercepts, across the 2 time points.
And Bengt, we're going to be putting topic 3 through 8 up on our website, hopefully very shortly. And topic 3 covers this type of a model, repeated measure factor model, multiple indicator growth, and shows the tests for testing measurement invariance across time. So all of the inputs and the steps to do that are in topic 3. So you can take that off the website, hopefully, within the next couple of weeks.
So in the longitudinal factor analysis situation, if you do this, if you find the sufficient invariance here, you can study changes in the means and variances of this factor across time. Final point, before we go to topic 2, is that we didn't tell you the full story of the excitement that's going to happen in version 5.1 coming out sometime in April. We think it's a bit of a revolution. But then again, I've been watching the HBO miniseries of John Adams a little bit too much. So what you can do in 5.1, if you like, you can impose this CFA structure here on this measurement part F3 and F4. But you can, if you like, impose an EFA structure on F1 and F2. You can have an EFA structure with rotation for F1 and F2 and still regress F4 on F3 and F3 on these factors. If you don't have this simple structure hypothesis of CFA, but only have a structure of, or hypothesis of there being 2 factors, but you would like the rotations to sort out what the factor structure is. You have a notion about it, you have designed it to measure 2 factors, but you don't want to impose these zeros that the CFA requires. You can let this be an EFA structure. Very easy by statement with a special twist to designate this as an EFA structure. And then you can still do the structural equation modeling. So you have the combination of the 2 worlds. And that, I think, will help in testing situations where often you reject the strong CFA assumptions, but you may not reject the EFA assumptions. So that's just a look ahead to what will come in the future there. So with that, I'm going to try to switch over back to topic 2. And the table of contents looks quite interesting. Relative to topic 1, we're going to spend a lot more time on the basic regression analysis because there are some less known concepts of regression that we want to take the time to discuss with you because it provides a great background for what follows in this course sequence. And we've talked about these slides yesterday, so I won't spend time on them today. I will instead go straight to slides 9 and 10 and just tell you a little bit about this and try to motivate you now. Some of you found yesterday quite accessible. Some of you found yesterday difficult. Some of you may have found that it went fast, and it did. I should tell you that there are a lot of introductory and intermediate structural equation modeling CFA type of courses in the US that you may want to attend if you found yesterday very difficult. So you may want to do that to prepare yourself for the next steps of this Mplus sequence. So we were here at topic 1 yesterday. We went from introductory to advanced pretty quickly. I would say that topic 1 gives a great background for topic 3 and 4, which are the growth modeling, longitudinal analysis topics taking place in August here. Because what you're going to do, what you're going to see when you go into growth modeling in August is that it's really a CFA type of model, CFA, SEM type of model that we're going to talk about with some twists and extensions. Today, we're going to be talking about a little bit less known areas, not linear regression anymore, but nonlinear regression for categorical and other non-normal outcomes. Topic 2 will then provide a great background for topics 5 and 6 on slide 10 in November at the University of Michigan, Ann Arbor. So we're changing venues there. And all of these topics then build on each other so that by the time you got into topic 6, you will have a great background for going multi-level in topic 7 and 8. Multi-level for all of these previous models that we have discussed will be integrated in a multi-level framework. So that's how we will march forward. So now let's get into the topic of today. And when we talk about categorical variable modeling, it's useful to make a distinction between working with only observed variables, which is where we're going to start, like in regression analysis. And later on, we're going to switch over to adding continuous latent variables behind these categorical observed variables. And a third topic, which we will not talk about here, but save for Ann Arbor, is when we have categorical latent variables behind the categorical observed variables. So you should be aware that when you have categorical observed variables, it doesn't mean that the latent variables have to be categorical as well. You can have categorical observed, categorical latent, or categorical observed, continuous latent, depending on your application and what you think is reasonable. And some of that is testable. You can make a distinction between them in statistical terms. So we'll talk about observed variables first, only observed variables, and just a couple of slides to familiarize ourselves with some basic statistics background and give you a couple of references for further reading if it is not familiar to you. So the idea of these courses is you can get a lot out of them if you have the right background. Like for this day, it would be great to have logistic regression as a background. If you don't have it, you will get a chance to catch up and learn what logistic regression is, but you probably can't catch everything, and therefore we will give you further reading suggestions. So after this day, you can go back and read an introductory book on it and be then prepared for when the more advanced categorical variable days come along. So let's take an example here, two examples, alcohol dependence and gender in the National Longitudinal Study of Youth. And it's good then to train yourself to, as quickly as possible, see what the table displays. We see rows of males and females, and the number of people here adding up to about 9,000. So that's, if it's on the left, it's often an X variable, and that's what it is here. You have not dependent, not alcohol dependent, and alcohol dependent classified individuals. Fewer of them in the dependent column. We can certainly compute a proportion. 0.056 would be 256 divided by 4573. You can check me. And 0.152 would be 699 divided by 4603. So within each row, you can look at the proportion that are alcohol dependent for each of the genders. And then we're going to introduce terms like odds. Odds is a very simple thing. You're familiar with it if you're a gambler. That's just the proportion divided by 1 minus the proportion. So if you take the proportion and divide it by 1 minus 0.056, you should get 0.059. Check it out. So that's the odds. And it describes the chances of observing dependence relative to not observing dependence. Proportion for males translates into an odds of 0.179. And then we can summarize that further into an odds ratio, which is the ratio of the male, say the male odds to the female odds. Comes out to be about 3. You could turn it the other way around. Actually, the balancing point, the neutral point, is 1. And what I mean by that is that the odds ratio is a measure of relationship between two variables, say two dichotomous variables. So the odds ratio is an association measure, like a generalization of the correlation for continuous variables. And correlation 0 translates into an odds ratio 1. So here, if we're far away from 1, if we divide the females by males, then we get far away from 1 from below. But in any case, this shows a strong relationship. So odds have to do with one dichotomous variable. Odds ratios have to do with two dichotomous variables. And then you can put wording on this. Males are 3 times more likely than females to be alcohol dependent. And this is from real data. Colds and vitamin C corresponds to a slightly different situation. Up here we do not random sampling, but complex sampling from a survey. But down here we have a randomized trial, and we say we're going to have half of the sample given a placebo pill and half of the sample given a vitamin C pill. One dropped out apparently. So the numbers are prefixed here. And the categorical variable analysis literature makes a distinction between fixing the numbers versus having them free. But in any case, you have the same basic calculations. You calculate the proportion of having colds and an odds for each of them. And you can compute an odds ratio to see if eating vitamins reduces your chances of having a cold. So just two kinds of sampling procedures. One thing you have to really be up on when it comes to categorical variables are probabilities. And we're going to look at three kinds of probabilities. One is the joint probability of two variables, u and x in this case. The other is a marginal probability, which is looking only at one of the variables, and in this case, and conditional probability is probability for a u outcome given that x is at a certain value. So this vertical bar is expressed as given x in this case, that is for x having a certain value. If you take the previous example on slide 14, I'm getting good exercise here, that if you take these numbers, and you may want to sit and do this with your calculator just to feel more familiar with these numbers, you can compute the proportions in each of the four cells. You know, you have a 2x2 table here, and the four cells then have proportions when you divide by the total sample size 9176. And these proportions add up to 1 in here. The not dependent and the dependent crossed with female and male. There's a round off error here with 0.01 off from a total of 1. But these are the proportions. That's the sample quantity, and in the population that corresponds to probabilities. That corresponds to the joint probability up here. Now the marginal probability, which in the sample then is the marginal proportion, sits here. What is the proportion in the sample that's alcohol dependent? 0.11 is the answer. So these are the marginal probability or proportions down here, sample counterparts to probabilities. Conditional, well, in this case we might be interested in u being dependence and x being gender, and then you calculate them out here. So how did I get 0.06? Well, that is the the dependent among females. 256 divided by 4573 is 0.06 if you round that 0.056 up, sitting out there. That is that's a sample counterpart to a conditional probability. Given that you're female, what's your probability of having alcohol dependence? And same thing for male. 0.15 is the 0.152 sitting over there on slide 14 for males. So joint probabilities adding up to 1, marginal probabilities for one variable, in this case u, the dependence variable, adding up to 1 except for a rounding error, and the conditional probabilities, which don't add up, but conditional probability, this is the conditional probability of dependence, and then of course the conditional probability of not dependent is 1 minus 0.06. So this is the conditional probability for dependence, and the other possible outcome is what the probability is for not dependent, and those two add up to 1. So the conditional probabilities add up to 1 for each of the two rows. And all of those concepts are going to come back and be recycled in various shapes and forms. I forgot to say one thing here. I have a little note. If you go back to slide 10, one thing I should add, for topic 5 and 6, if you can't bear to wait until November, we will have a one-day preview of this topic, one-day summary of this. So topic 5 will be the morning and topic 6 will be the afternoon. At the Psychometric Society meeting in New Hampshire on a sunny day, Sunday at the end of June, near the coastline of New Hampshire. I hope it does have a coastline. So it's not like oceanfront property in Arizona, right? Not like that. So that you can do at the Psychometric Society pre-session on that topic of categorical latent variable modeling. By the way, I'm also giving a keynote address on this issue of exploratory structural equation modeling that I'll keep alluding to is in 5.1. I gave a talk on that Monday at the biometrics meeting. So, yeah, so that will be at the Psychometric Society meeting. I gave a talk on it at the biometric meeting Monday, and it will be an extended version at the psychometric meeting on the Monday of that meeting. So let's see, where are we? Getting back to the story then, we are on slide 15, and we're going to slide 16. Slide 16. Actually, I think I had one more point on slide 15. Slide 15, start to flip you around here. So at the bottom of slide 15, a couple of more terms. 0-1 variables are called Bernoulli variables by statisticians who want to have these fancy-sounding terms so they can charge more in their consulting. And it's a variable as 0-1, for instance. And the expectation, the population mean of that variable is pi, not 3.14, but the pi that's the population probability of observing a 1. And sometimes you look at sums of Bernoulli variables, and then you get into so-called binomial distributions. That's for dichotomous variables, and when the variable has more than 2 categories, unordered categories, nominal variables, you talk about a multinomial distribution. This 2-by-2 table can be seen as a multinomial with 4 cells. The number of parameters are the number of cells minus 1, because the number of parameters are actually the probabilities of being in these cells. In this case, maximum likelihood estimation is very easy, because the maximum likelihood estimate of a probability, like this one, of that joint probability, the maximum likelihood estimate of that probability is the sample proportion, which seems very intuitive, right? And that's what maximum likelihood gives. And in multiple group analysis, you have so-called independent or product multinomials. And with count outcomes, we talk about Poisson distributions. So those are some terms, and here are some more. Cross-product ratio, we talked about it already. We talked about an odds ratio. In a 2-by-2 table, 2 binary variables, x and u, you have 4 probabilities. These are joint probabilities adding up to 1. And the cross-product ratio is another name for the odds ratio, because it's formulated by multiplying the diagonals, that times that divided by that times that, as you see on the left here. That's a statistical way of saying expressing the cross-product ratio. But what does it mean? Well, it means you look at the odds of alcohol dependence relative to not alcohol dependence for males. That's that over that. So pi 11, you can look here now, over pi 10. And then you do the same thing for females, dependent, not dependent, and take the ratio of them there. And that odds ratio expression here is the same as the cross-product ratio written there. See, so to remember it, you just do that times that, divided by that times that. But a more intuitive is that divided by that, and that thing divided by that divided by that. And that's what this says. This is just to wake you up in the morning. And so you have odds ratios, but then you talk about log odds ratios. Why do statisticians switch to logs, which are so hard to deal with? Well, because an odds ratio has a distribution, a sampling distribution, which is not really closely related to the normal. But if you take the log, you get an approximate normal distribution. And statisticians like that. So we're going to talk about log odds ratios. So instead of the neutral point being 1 for no association, we take the log of 1, which is 0, and bring back 0 as the no association point, just like a regular correlation. So there are some advantages to it. Log odds ratios, we're going to work with that in the logistic regression context. And then we have tested proportions, Pearson chi-square, and likelihood ratio chi-square. So those are a set of terms now that you will find in these books. So in the US, I believe that this second book is quite popular. I know that, for instance, Michael Sobel teaches from this book at Columbia University. This is Agresti Light, and this is Agresti Heavy. Agresti writes very well. Another person who writes very well is Scott Long. And he has a lot of technical detail, but also writes it in a pedagogical fashion. So if you're a little bit more statistically inclined, but still like the helpful words, this is a recommended book. And here's a pretty standard logistic regression book if you want to just focus on logistic regression. Logistic regression being just one little part of categorical data analysis, but a key part. All right. So what we want to try to cover here is some key aspects of logistic and Probit regression. Dichotomous outcome first, then covering the idea of adjusted log odds, then go from dichotomous outcome to ordered polytomous outcome, and then to unordered polytomous outcome, and then to multivariate categorical outcomes. So here, ordered polytomous, you might want to write that that's an ordinal variable. And for unordered, that's also given the name nominal variable. So this is low, medium, high. This is taking the bus, the train, or the bike to work. We try to throw in these social messages as we go along. So now we're going to slow it down a little bit, although it's all relative, and try to make friends with logs. So we're going to talk about a lot of different logs here. Certainly, they're going to come back again and again through these 8 topics. One log is a very different log than the topic of today, but still it's a part of the logarithmic function, which comes up in the context of maximum likelihood estimation. Maximum likelihood estimation maximizes a likelihood, but again, statisticians don't like likelihoods as much as they like a log of likelihoods. Again, taking the log simplifies the mathematics or the statistics of things, although it tends to drive non-statisticians crazy, but statisticians don't care that much about that. So what is a logarithmic function? Well, it has to take, sometimes we use the E log, E being then the natural log. You can have 10 logs too, if you remember from your elementary school studies, or maybe it's high school. Anyway, so the argument then that you take the log of is x, and it has to be positive. You don't take logs of negative numbers. So then if x is 1, we said the log of 1 is 0, so that sits there. And a log of something that's less than 1 is negative. And log of something that's greater than 1 is positive, and it's sort of a retarded increase here. But what we're going to see in maximum likelihood estimation, we're going to spend most of our maximum likelihood analysis life down here in the negative. So we're going to have like negative 100 here, negative 500 down there, and we're going to be much more happy if we get a log likelihood of negative 100 than negative 500, because negative 100 is higher up than 500. But we're going to be forced to work in that negative scale. But when you look at those likelihoods, you will then think about that picture, right? Or maybe not. So that's one thing. That has to do with maximum likelihood estimation. Now, the logistic, that also starts with a log, but the logistic distribution function is something different. When we talk about modeling categorical outcomes like binary U, dichotomous or binaries, I'm going to use both words, U equals 0 versus U equals 1, we focus on one of the outcomes, alcohol dependence, for instance. And we want to model not the value of U. 1 and 0 are not quantitative values, but more labels for the outcomes. We could have said U equals A, U equals B, and it would have been far more pedagogical. But what we want then is a probability, describe how the probability of alcohol dependence changes as a function of X. X being, say, age of first drink. So as X changes, the probability changes, but we have to keep the probability between 0, which is here. You might want to write a 0 right there on slide 19, top right. And it goes up to 1, but it can't be higher than 1 because then it's not a probability. So to make that probability between 0 and 1, we have to have this S-shaped non-linear curve, and that is then a conditional expectation function. Linda talked about that yesterday morning. It's a conditional expectation function. We talked about E of U being pi, and that's what we're talking about here. Yesterday, Linda talked about a linear expectation function, but here we have to have a non-linear one. So that's a distribution function, and you have a lot of distribution functions for any kind of distribution has a density and a distribution function. The density sits down here. There's something called a logistic density. It looks like a normal, like a bell curve, but it has slightly fatter tails. But it is a distribution that's quite respectable, and any distribution then has a density and a distribution function. Distribution function having to do, well, we'll get to that. Now, some people then don't like to be in a nonlinear framework. They are much happier if things are linear. Well, you can make this curve linear by taking the logit of the probability. Taking the logit of the probability. So we're going to take the logits of probabilities, it's a transformation. And we're going to tell you in utter detail what the logit is. But for now, all we need to know is that it makes the curve linear. And then we can think like we think in linear regression terms. Here's what the logistic distribution function on slide 20 looks like. Explicitly, we drew the curve on the left, but here's the equation. And it's a very simple equation that you can actually evaluate on your hand calculator. It looks like this: 1 divided by 1 plus E, that's the natural E, yeah, to the power of minus parenthesis beta 0 plus beta 1x. So somewhere in the bowels of this expression, you have a linear regression function. No residual, but you have the intercept beta 0 and the slope beta 1 times the predictor variable x. So it's a nonlinear function f of that argument beta 0 and beta 1 plus x. And very shortly, we will find that the linear part here, in parentheses, what I call the argument, is a logit. It's called a logit. And it's linear. That little linear part is actually what we're looking at, bottom left on slide 19, is linear in x. Logistic distribution function, any distribution function has to do with if you are at a certain x value, what's the probability that you are, well, actually look here instead. If you are at a certain x value, what's the probability that you are to the left of that x value? Or rather, at a certain point, what's the probability of being below that point? And that is, this area under the curve is the distribution function value that we look at the left. So as this value here moves to the right, the probability goes from 0 up to 1, right? You have more and more of the curve to the left. So that's the definition of a distribution function. So you go from the density on the right to the distribution function. Density actually has a proper density, and with variance, that is pi squared over 3. And here, pi is 3.14. It just happened last week, right? 314. student of mine told me. Too much time on our hands. Pi squared over 3 looks, you know, like a nerdy thing, but you're going to see that that's about 1.7, 1.8 if you evaluate it. Or maybe it's the square root of it, that is. But we're going to see it come back several times. You have the same situation for Probit regression. It also considers a nonlinear function between 0 and 1, because it's also a distribution function. It's a normal distribution function. So we go from the normal density and ask about the probability of being below a certain point, the shaded area of the curve, and that is then the value on the y-axis in the distribution function. But in any case, it is a nonlinear function of beta 0 plus beta 1x. This thing here in equation 60 is phi, cap phi, or phi, the Greek phi, which is the symbol for the normal distribution function. So the way to think about it is that this inside here, beta 0 plus beta 1x, is now a z-score. If you think about the table in the back of your Stat 101 books, this is a z-score that's in parentheses, and when you take phi of the z-score, you get the probability. If you go the other way around, if you start from a probability in equation 60, if you start from here inside the bracket and want to ask what the z-score is, you go from probability to a z-score, well then you take the phi inverted, the opposite inverse function. That's how statisticians like to write that. So phi inverted times phi is identity link. Ignore me. That's actually your line, right? So now, how serious do you have to be about logits and their coefficients? Well, you can have different levels of engagement here in the topic, from being pretty lax and relaxed in bullet 1 to getting more heavy as you get to bullet 2 and 3. We're talking about slopes here. All you may want to be interested in is the sign and significance of a slope, the beta 1 that we're talking about, multiplying x. Sometimes you want to be a little bit more elaborate and talk and interpret the model results from a logistic or probit model in terms of odds and odds ratios. Perhaps you feel that that gives a more intuitive understanding of the results. Sometimes you want to be really down to earth and see and explicate what the estimated model implies in terms of the probabilities for the outcome as a function of different x values. And we're going to do all three of these. We're going to do, first of all, we're going to go through this page on log odds. And it will be a page that at first you don't like, but later on you're going to love it. So just repeat again, at the top of slide 23, odds for the event of u equals 1 given x. What was the odds again? Well, now we're going to do it not in the sample, but in the population. That was the probability of u equals 1 divided by probability of u equals 0. U equals 0 being 1 minus u equals 1, right? I think we expressed the odds in the proportion example as 1 minus the odds. This is the odds of dependent, and this is the probability dependent, and this is the 1 minus the probability of dependence, because the two probabilities u equals 0 and 1 add up to 1. So the two ways of expressing the odds, here's one of them. There's the other. So that's the odds. Keep that in mind. Now, we said we're going to work with the logistic function. That's what we do in logistic regression. The logistic regression tries to express the probability of u equals 1 of alkyl dependence as a function of x through this mathematical formula, which is an S-shaped formula form. Why do we choose that? Why is that so popular? Because it gives an log odds that is linear in x. How does that happen? Well, log odds is the same as a logit. So logit is equal to the log of the odds of u equals 1. The odds of u equals 1 is at the top of the page. So we just insert the top of the page into the bracket here, right, for the probabilities. And then we express the probabilities in terms of the logistic function here's the probability u equals 1, and here's divided by 1 minus probability u equals 1. And if you play around with that with simple algebraic rules, out comes log of the bracket at the end of slide 23, log of e to the power of this beta 0 plus beta 1x, and log of e cancel each other out, and you get beta 0 plus beta 1x. So the log odds, which is the logit, is the beta 0 plus beta 1x, the argument sitting here. So that's just proving that that is the log odds sitting in there. And we're going to be able to, therefore, keep this simple form for the log odds and make our results, therefore, more easily interpretable. So there you just have the formulas for it. And to repeat, logit equals log odds, slide 24, equals beta 0 plus beta 1x. That's a summary of the previous page. And in words, when x changes 1 unit, the logit, or the log odds, changes beta 1 units. That's what that says. And if you don't want to have, this is having like the dependent variable being a log odds. If you don't like the log, then you change the phrase to when x changes 1 unit, the odds changes e to the power of beta 1 units. So you take the exponent of the beta 1. Taking the exponent is something you can just click in on your hand calculator. And typically in the regression program, certainly in Mplus, logistic regression gives you both beta 1 and e to the power of beta 1. And with that, I think it's time for an application.
Okay. You do it the way you like it.
This is how you want it, right?
Sure. Well, okay. All right, let me just come over here and change this. All right, so what we're going to do is look at a couple of examples now and try to apply what Bengt has just taught us all. So the first example we're going to look at is shown on the left screen, the British coal miner data. We're going to look at that. The dependent variable is, have you experienced breathlessness? So people either answer yes or no. And on the y-axis of the diagram, we have the proportion yes. And on the x-axis, the covariate is age. So we want to look at the have you experienced breathlessness as a function of age? And if we look at this, the scatter, so the data points are in red squares. And if you try to fit a line to this, you can see that it really doesn't fit well. The line overestimates in the middle of the age range, and it underestimates at the upper and lower ranges. So here we have overestimation if we try to fit a linear, and here we have underestimation. Now, if you note, it looks very much like an S-shaped curve would fit that quite well. So we're going to take a look at what would happen if we take the logits. What happened to my thing, Bengt? Oh, there, okay. So here's, you stole it from me. So here's the plot. So here's what happens if we turn our data points into logits. And you can see that then a line fits much, much better. So it would seem that a logistic regression model might be a good approach for this data, better than trying to fit a linear model, certainly, or maybe a Probit regression model. So what we did here, and just to remind you, the sample logit is the log of the proportion divided by 1 minus the proportion. So that's how we change the data points into logits. So we have logit on the y-axis, age on the x-axis. So then what we did, if you take a look on the right screen, is we, just to illustrate what happens if you use ordinary least squares regression versus logit or probit on this data. So the first column shows age. Then we have the number of observations in the second column, and then the number of observations, yes, in the third column. So that's the number that experienced breathlessness in the third column, and the proportion that experienced breathlessness in the fourth column. And these proportions would be equivalent to model estimated probabilities, which we are going to show in the last three columns for linear regression, for logistic regression, and for Probit regression. So if we take a look at the probabilities, the model estimated probabilities, if we do a linear regression on this data, we can see the same thing we saw in the picture. We have overestimation, so we're comparing the proportion yes to the estimated probabilities. So we have underestimation for the first two values. In fact, we have negative estimates, and that's not even allowed. A probability can't be negative. Then we have overestimation, as we saw in the picture, 0.061, and we estimate 0.094. 0.149, we estimate 0.192. So we can see that the linear regression is not capturing the data. If we go to look at the logistic regression in the next column, we see that we do a somewhat better job. At least we're not negative, but we still overestimate 0.008, 0.013, 0.018, 0.022, then 0.035, and we do pretty well here with 0.36. And in the middle ranges, we do quite well, but at the ends, we don't. For Probit regression, we do quite well. So 0.008 versus 0.009, 18 versus 18, 35 versus 34, et cetera. And if we look at the chi-square, which are at the bottom of the screen here, we see that the logistic regression has a chi-square of 17.13, whereas the Probit regression gets the 5.19. So actually, the Probit regression fits better than the logistic regression in this case. And although logistic regression seems to be more popular for whatever point of view, I think because it uses maximum likelihood in most cases, oftentimes Probit regression is a good alternative and may actually fit the data better, as we see in this example. Now we're going to actually analyze the coal miner data using Mplus, both Probit and logistic regression. But first, I just wanted to show you the data, because it has a special feature that you may have data that have this feature, and just to let you know that you can use it. So the data isn't given for individual observations. In our data set, we have, for the X variable age 20, the first entry in the data set is for age 22, U0, so not breathlessness, and then the number of people who experience this. The second line in the data set is for age 22, U1, or breathlessness, and then the number of observations that have that. So and then same for age 27 has two entries, one for 0, one for 1. Age 32, the same thing. So this data is in a frequency format, and we can specify this in Mplus and analyze this data without creating a big data set that has a single entry for each observation. Okay. So let me have a drink. Okay, so now before we get into the input, let's talk about special options in Mplus for categorical variables. So first of all, the categorical option. That's used to specify the dependent variables that are categorical. And by categorical, we mean either binary or ordered categorical. So there's some order in the data. And all we do is we just say in the variable command, categorical are, and then we give the variable names, U1, U2, U3. We usually refer to categorical variables as U and censored variables as Y and continuous variables as Y. So any type of categorical variable, we usually say U. So in our examples in the user's guide, for example, and in any diagrams we make. So now, when we move into the realm of categorical variables, we don't have intercepts or means as we do with continuous variables, but thresholds. And thresholds are related to intercepts by a difference in sign. So if we have an intercept for a categorical variable, it's equal to the negative of the threshold. And we need a way to refer to thresholds in the model. Because with a binary, for a categorical variable, they have the same number of thresholds as there are categories minus 1. So a binary variable has 1 threshold. If you have an ordered polytomous variable that has 3 categories, it has 2 thresholds. 4 categories, it has 3 thresholds. So we need to be able to refer to these thresholds in the model command, so we have to have a convention to do so. And the convention is that we add the $sign after the end of the variable name. So the number of, and as I said, the number of thresholds is equal to the number of categories minus 1. So U1 $1 refers to the threshold 1 of U1. U1 $2 refers to the threshold 2 of U1. So U1 would be a categorical variable with 3 categories, and you need to refer to 2 of them by U1 number or $1, U1 $2. So you would refer to those in bracket statements in the model command, and we'll see that as we go on today. Now, if U2 is a variable with 4 categories, likewise we go U2 $1, U2 $2, U2 $3 to refer to thresholds 1, 2, and 3 of a 4 categorical variable. And if we just have a binary variable, then it would be U3 $1 because they would just have 1 threshold. Now we have scale factors, and they're referred to in squiggly brackets. And we're not going to talk about those now because they're only for Probit regression when you have either a multiple group setting or a longitudinal setting. And when we get to multiple group analysis this afternoon, we'll talk about those. So I'm putting 2 inputs here. So we're going to analyze this data using both logistic regression, which is on the right screen, and Probit regression, which is on the left screen. So some new things in the input, the categorical option in the variable command. So we're saying categorical equals U being breathlessness. And then we have the frequency weight, freq weight option. So frequency weight equals W. So you give the variable in the data set that gives the frequency weight, or the number of observations that that line represents. So if line 1 represents 1,000 people and line 2, 2,000, then that variable that specifies that in the data set is the frequency weight variable. Now in the define command, we are dividing x, which is age, by 10. So we say x equals x divided by 10. In the analysis command, we're specifying the estimator equals ML. So we're asking for maximum likelihood estimation. And in Mplus, if you do maximum likelihood estimation with categorical outcomes, then you get logistic regression by the default. You can also use the link option in the analysis command to say link equals Probit. Then with maximum likelihood, you can get Probit regression. So, but here we're not saying anything about the link option. We're just saying estimator equals ML. And then in the model command, U on X. So we're regressing the breathlessness on age. And then we have just asking for standard things in the output command. So this is how you specify the input for logistic regression. You took my notes. OK, so now the input for Probit regression. Well, in Probit regression, so this input is identical to the logistic, except we don't have our analysis command. So we don't specify estimator equals ML. When we don't specify estimator equals ML, the default is a weighted least squares estimation. And weighted least squares estimation with categorical outcomes gives Probit regression. So now here's the, let me put the Probit, no, let me not do that. Okay, so let's take a look at the results from the logistic regression. So once again, we've seen results. We know that we have the column, the first column's the estimate, then the standard error of the estimate, the ratio, which is a z-score, and in version 5, a p-value. So here's the regression of u on x. This estimate is a Probit regression coefficient. A logistic, sorry, I'm in logistic here. I'm still sleeping. I finally slept last night. I haven't woken up yet. So here's a logistic regression coefficient. And then we have our threshold. Now with logistic regression, you can get your odds by exponentiating the regression coefficient, 1.025. So we take this logistic regression coefficient and we exponentiate it to get an odds. So we interpret this as x increases 1 unit, and 1 unit for us, because we divided age by 10, is 10 years. So as x increases 10 years, the odds of breathlessness increases 2.79. And logistic regression has a constant odds that we'll be talking more about. So whether it's the difference between 42 to 52, or 52 to 62, or 62 to 72, the odds of breathlessness is going to increase 2.79. So this, now here we see, Bengt said there's various levels of engagement here. So here we could just say the relationship is positive and the relationship is significant. Or we could turn this into an odds, or as we show in the next slide, we could turn this into a probability. So Bengt showed you all of the formulas for the various types of probabilities. So here we have the probability of u equals 1 given x. Actually, I want to put something on the other screen before I do that. Okay, so we see where the numbers come from. Oh, well, that's true. So anyway, we have the probability of u equals 1 given x is equal to 1 over 1 plus e to the minus l, the logit. And we know, you've seen that formula. And what is the logit? It is beta 0 plus beta 1 x. So, and beta 0 is an intercept. So we have a threshold. The threshold is a minus intercept. So we put a minus sign in front of this. The logit equals minus 6.564 plus 1.025 times x. And here's where we get the 1.025. And we're going to evaluate this. As Bengt said, the probability has to be evaluated at a given x value. And we're going to do that for 6.2, which is actually age 62. So the logit is equal to minus 6.564 plus 1.025 times 6.2, which is equal to minus 0.209. If you do the probability formula, 1 divided by 1 plus e to the minus, so then it's e to the 0.209, we get a probability of 0.448. So a probability of experiencing breathlessness at age 62 of 0.44 or 0.45. Okay. Now, on the right screen, I'm going to show you the Probit regression results. And you can do the same thing here. They're in different scales, the Probit and logistic regression. So the parameter estimates values are not going to be the same, but the third column, the ratio of the parameter estimate to the standard error should be they should be the same. They should be significant or not. There is, and we'll be talking about their relationship as we go forward here. So if you look at sign and significance, we find the same thing we found in the logistic regression, a positive relationship between breathlessness and age that is significant. Now, with Probit regression, we can't exponentiate the Probit regression coefficient to get an odds because we don't have a situation of constant odds there. So we can't take that step of going from sign and significance to the odds, but we can turn it into a probability. And the right screen shows how to do this. So Bengt showed you that it's using the normal distribution function phi of the beta 0 plus beta 1x. And if you work through this, you find out that that's phi of minus tau plus beta 1x. Beta 0 is the intercept, and the negative of the intercept is minus tau plus beta 1x. And we can, let's just go back to the results so we see where the numbers come from. I'm happy because I get to go home today. He doesn't. So let's see. Here's the Probit regression results. OK, so over here, so let's see where we get this. Here we have our threshold. So we have minus tau, so minus 3.581, plus, here's our regression coefficient. This is a Probit regression coefficient, 0.548 times 6.2. And you get the number 0.427. Oh, OK. So we get the z score here, minus 0.1834. And then we evaluate that on a z table, using a z table, and we get a probability of 0.427. So that's very close to what we got, 0.448 or whatever it was for the logistic regression. And you wouldn't expect to get totally different results. I mean, they would be very, very similar. It may be that one model fits slightly better, but the general conclusions you're going to draw should be the same. And so what is the relationship between these two? Well, the logistic estimated regression coefficient is approximately equal to the Probit estimated regression coefficient times c, where c is the square root of pi squared over 3, or the logistic density, and that ends up being 1.81. So if you multiply the logistic regression coefficient times 1.81, you'll get approximately the Probit regression coefficient. And sometimes people think they can do that, and then they can exponentiate it. But it still doesn't work that way. So even though you put it on the scale of the logistic regression coefficient, it still isn't a logistic regression coefficient. So it can't be exponentiated. OK, so now what we're going to do, we talked about an example with a single x. And so what we want to do is now extend that to Probit and logistic regression that have two x's, one binary and one continuous. And we want to do that because we want to show what happens with two x's because they're controlling for each other in this regression. It's no longer a simple case with one covariate. So I think you're familiar with this formula 22 pretty much by now. The probability of u equals 1 is now going to be given x1 and x2, so given two x's. And it's a function, and we're using f now to represent both the logistic distribution function, if we want a logistic regression, or the normal distribution function for Probit regression. So this is a generic way of referring to it. And it's a function of the logit, which now is beta 0 plus beta 1 x1 plus beta 2 x2. And as I said, f is either standard normal or a logistic distribution function. So the example we're going to talk about is lung cancer and smoking among coal miners. And smoking, lung cancer, of course, is the dependent variable. Smoking is X1, and X2 is the years spent in a coal mine.
Another social message.
Right, another social message, as Bengt says. Well, hopefully, I was going to say, I hope that. Let me just see. Yes, okay. So here are some pictures similar to what you've been seeing. So on the y-axis here is lung cancer, the probability of lung cancer. And X2 down here is years spent in the coal mine. And the curve X1 equals 1 is smokers, and X1 equals 0, non-smokers. So we see our S-shaped curve once again. And we can, so for a given age, the probability of having lung cancer is lower for non-smokers than for smokers, if you follow this line. If we take either the Probit or Logit, so we can turn these S-shaped curves into either Probits or Logits, depending on whether we're doing logistic or Probit regression, we get these parallel lines that we've been seeing yesterday and today. So X1, the higher line is the smokers, and the lower line is the non-smokers. And age is on the x-axis. So as age increases, the probability of lung cancer increases, and at a constant odds. So we'll keep this diagram here. Okay. So we have the two covariates, as we mentioned. And we just saw this formula earlier. The probability of U equals 1 given both of the covariates has a logit that includes both of the covariates. And that implies a log odds of beta. The logit is the same thing as the log odds. So the log odds is beta plus beta 1 x1, beta 2 x2. Then we can get the log odds for x equals 1 and the log odds for, or x equals 0 and the log odds for x equals 1. And what are those? Well, for 0, it's beta 0 plus, and then if this is 0, it drops out, so beta 2 x2. And the log odds for x equals 1 is just beta 0 plus beta 1 times 1, so it's just beta 1, plus beta 2 x2. So then we have our two log odds, so then we can turn them into a log odds ratio. So we're going to get a log odds ratio for U and x1 adjusted for x2. So when you have more than one covariate, things are adjusted for other covariates in the model. So a log odds ratio is equal to the log of the two odds, which we have over here, which just happens to be the difference in the two odds mathematically, which ends up being beta 1. So the odds ratio, or the exponentiation of beta 1, is constant for all values of x2. So if you don't, and you may not believe that it's constant. You may think that after you spend, when you first go into the coal mine, it may not be that the effect is the same as when you've been working there for 30 years. So you may not believe that, that the odds ratio is actually constant for all values of x. You may believe there's some interaction between x1 and x2, smoking and years in the coal mine. And if you introduce that interaction, then the constancy of the odds ratio no longer holds. But let's say that we say we believe that this odds ratio is constant for all values of x, then how would we interpret it? We would say the odds of lung cancer adjusted for years in the coal mine is whatever the odds ratio exponentiation of beta 1 value is, times higher for smokers than non-smokers. Or the odds ratio adjusted for years is. So you have to take into account that this adjustment in the interpretation of this data, of these results. Okay, so now we're going to take a look at another example. And this is going back to the, I'm just going to open this up for a minute. Okay, so we're looking at the NLSY data, and we're going to look at odds ratios for alcohol dependence and gender, adjusting for the age first started drinking. Okay, so we have in the first column age, we have frequencies, so this is just from the data. So from our raw data, we have the frequencies of age by male and female. So we have 85 observations in our data set, age 12 or younger, who are females, and 223 that are male. We have 105 females in the data set that are age 13 and 180 males. So this is just your data on this half. And then from the data, we have our observed odds ratios that we can compute. So the proportion dependent for females and males, females in this column, males in the other, and we can create an odds ratio. And how do we do that? Well, the odds is p times 1 minus p. So we get an odds for females and an odds for male, and then we take the ratio. So in this case, we put males divided by females, and we come up with 3.98. So if you take 0.071 divided by 1 minus 0.071 and 0.233 divided by 1 minus 0.233, and then take the ratio of males to females, you should get 3.98 if we didn't make a mistake. But I checked it, so I think it's OK. So anyway, so that's how we get the odds ratio in the data. So, and this is just, so in the data. But then we can estimate these. And when it's in the data, you can't adjust for another covariate like age first started drinking or something. So in the data, instead, you can estimate these, and you can estimate the probabilities and odds ratios using logistic regression or Probit regression. So here we want to take a look at how the results look. Now, for logistic regression, we mentioned that the odds ratio is constant. So we do the analysis, we get our logistic regression information, and we can compute we get the constant odds ratio of 0.266. For females, we don't, there is no odds ratio constancy assumed, but we can compute an odds ratio from the model estimated values for each age range and see they're not constant. And when you take a look at the constant odds ratio versus the one that isn't constant, you can ask yourself the question, you know, is that constant odds ratio a restriction on the logistic regression model that may make it not really appropriate for the data? Because I think somebody could make a case for that. So what do we see with the Logit model versus the Probit model? In this situation, the chi-square for logistic regression is 54, and for Probit regression, 46.8. So the Probit model does have a lower chi-square. You know, it's hard to say if it's that much, enough lower to make the model fit that much better. I mean, both models probably fit the data well. But this is just really to bring to your attention the fact that logistic regression does have the assumption of the constant odds ratio. And do you have any other comments on that? No? Okay. Just to make sure I haven't forgotten anything. All right, so that's that. And we're going to look at one other situation, and then I think we could maybe take questions and then have a break. But the one, and once again, I'm going to put the left screen is going to be the observed data, and the right screen is going to be model estimated information. Okay. So in this situation, we're looking at data from the sources down at the bottom here, the U.S. Department of Educational National Center for Education Statistics base year and first follow-up surveys. So this is taken from that. And what we have here are 3 dependent variables. This is from the NELS data. We have below basic mathematics, below basic reading, and dropped out. And we have sample information regarding 3 covariates: gender, race, and socioeconomic status. What we're particularly interested in is these odds ratios, because when we look at it in the observed data, there is no adjustment going on. And so if we look at dropping out, then it would appear that ethnicity, the odds ratios are significant for Hispanic versus white, black versus white, Native American versus white, and also for socioeconomic status, low versus middle, high versus middle. So these are not unadjusted odds ratios. We're in the data, and they're unadjusted. But when we actually do an analysis and do a logistic regression, then what we find is we have adjusted odds ratios. So the odds ratios for race are adjusted for socioeconomic status and gender, I guess. And what do we see here? If you adjust race for socioeconomic status, these odds ratios are no longer significant. So this is just basically to point out how different things can look when you look at the covariates one at a time versus looking at them and allowing their relationships to be taken into account. And then I think that we should take questions. Do you agree?
Yeah.
Okay.
Good. So that's a lot of new material for those of you who have never studied things like logistic regression. But just remember, yes, we can. Let's hear it. Anyway, so let's hear. Do we have any questions? Yes.
So when you run this logistic regression in Mplus, when you use the complex survey data, where you have to use the strata and the sampling weight, is it the language the same?
Yes. So the question is, if you have complex survey data with weights and stratification and clustering, does anything change? Well, what you have to say is type equals complex, and then the estimator is MLR.
Well, you would have to say type equals complex. Yeah, right. You would automatically get MLR. But you would have to say a cluster variable, so cluster equals whatever your cluster. And then if you have a weight, you'd have to say weight equals and give the weight variable. So if you look in the user slide in the index complex survey data, there's a section that summarizes all the complex survey data features of Mplus. So you would have to tell us you have complex survey data. So like we ignore this in the NELS for illustration purposes.
You use both the frequency weight and the sampling weight.
No, right.
The question is, do we use both the frequency weight and the sampling weight?
I'm not sure that you can use sampling weight and frequency weight together.
Yeah.
I don't think you can. I think you can only use sampling weight with raw data.
But I think you're alluding perhaps to the fact that using frequency weight is not sufficient. It's using the sampling weights that's the key.
Right. A
Because
frequency,
some programs only use frequency weight approaches, and that doesn't adjust the standard errors properly for the
frequency
complex survey.
freq weight is simply for data manipulation. It has nothing to do with complex survey problems.
That's why Linda gave it two different names.
Right. Okay.
Yes.
Just have a question about threshold concept and intercept. I mean, why use threshold concept rather than intercept? Because it seems to be that it does make sense if you conceptualize a categorical variable, a categorical observed variable as the indicator of a continuous latent variable, which makes sense to use the threshold concept. And if that's the case, then the second question is that why a negative sign? Because to read that, it depends. You look at probability below the threshold or above the threshold. You don't have to reverse the sign. So could you please just say a few words?
Yes.
Yeah, so the question is about, and I wanted to emphasize that too, the question is about this matter of thresholds and intercepts, and what's the difference and what does it mean? We should emphasize that, and we'll do that now, as we switch from the dichotomous case to the polytomous case, these distinctions become clearer. So Mplus works with thresholds instead of intercepts when you have binary or ordered polytomous, ordinal variables. And I have the slide here, 46, which we'll get into, where the threshold concept becomes natural. I won't say anything more than that because we're going to talk about it. But when you talk about unordered polytomous variables, the threshold concept is not as natural as the intercept concept. So we're going to make that very clear now as we switch gears into the polytomous case. So I'll leave it at that for now. Yeah.
Yeah, on slide 34.
Slide 34.
Why did you put a negative sign in front of the beta 0?
That's why did we put the negative sign?
In front of the beta 0?
Yeah, this isn't 6.564 is not beta 0. It's the threshold, the tau that Linda talked about. So again, the threshold is equal to tau is equal to minus beta, or they have opposite signs. So we just add the negative sign there.
Isn't tau in the Probit? That's logic. And that's logistic.
This is logistic, yes. Right. Did you ask about Probit?
No, I thought that tau was not in the logic.
No, tau is an operation for both logit and Probit. The distinction between using tau, the threshold, or the intercept is a distinction between ordered versus unordered polytomous. And in the binary case, we see that as a special case of the ordered, so we keep the threshold in the binary case.
And in the output, it's labeled as a threshold. So when it's labeled as a threshold, then if you need an intercept, you have to take the negative value. And we label them threshold or intercept. I mean, we don't try to make you remember which is which. We actually tell you which one you get. Oh.
Yeah.
You'll next, okay? Oh, okay, it's the same. Let's wait because it's the same slide.
Slide what?
34.
That's up here.
If you go down to the last line, the 1 over 1 plus e to the 0.209, you said that's actually minus 0.209. That's what I was in the line before that.
So the question is about slide 34, and we get a positive sign in the exponent because negative plus times negative is, or negative, yeah, is positive.
But or do you have a question on the slide before you say?
This was
Okay.
it. That was it. Okay, so
42?
Slide 42.
The logistic regression
So the
model.
question is, why are the odds ratios the
Oh.
same on slide 42 here for the logistic regression estimated model.
Well, because the logistic model is estimated under a constant odds ratio. So the logistic regression model has that assumption. That's built in, right? It's built into it. And the constant odds ratio happens to be 2.66.
Just to add to that, I think that's one of the reasons logistic regression has become so popular relative to Probit, because it has that simple feature that the adjusted odds ratio, this is the odds ratio for gender relative to alcohol dependence, adjusting for age first started drinking. And the logistic model implies that constant odds ratio. Seems very simple and very easy to interpret, but it may not fit the data, and that's what we illustrate by Probit, which does not imply a constant odds ratio. You can compute the odds ratio based on the estimated Probit model, but it's not going to be constant. And in this case, it happened to fit the data better. So it's an embedded assumption in the logistic regression, which you may not be aware of. So we just wanted to bring it out here. You pick the next question, please.
Okay.
So is there a way to like use the logistic and the Probit to determine like a goodness of fit of the each assumption, where you say, you know, is like if you're looking at data over time and you want to see if the odds ratios significantly change over time, is there a way to use the Probit to say, you know, that there is a significant change in the odds ratios over time?
So the question is about odds ratios changing or not changing over time. Can you use Probit to evaluate whether the Logit assumption of a constant odds ratio is valid? One way is to look at the fit to the data. And here, this is a frequency table fit. Chi-squared says sub p, which is the Pearson chi-square. So observed minus expected divided by expected, where expected is the model estimated. 12 degrees of freedom having to do with the number of cells in the table, which corresponds to the number of parameter of the H1 model, the unrestricted model, which we talked about yesterday. And the unrestricted model is the multinomial model that we talked about this morning, where we estimate the parameters by the proportions. And the H0 model is our Logit model, which has these three parameters, I guess it is, beta 0, beta 1, beta 2. 12 is the difference between the number of parameters in the multinomial unrestricted H1 minus the number of parameters, the 3 of the H0 logistic model. So I guess that contrasting it with data would be one way to look at it. Now, the fact that Probit doesn't have a constant odds ratio may not be something to comfort you, because there is another, the Probit has some sort of function assumption about the odds ratio. It's just not the constant one. But the Probit model has its own structure. Anyway, next.
What would happen if you added another covariate? Can you still use the Probit model, or at that point you have to assume when you have multiple predictors that you're
So the question is on slide 42, what happens if you have more x variables or third x variables? Can you still work with Probit, or do you have to switch to Logit? And no, both models can handle as many x variables as you want. There's no restriction on that.
How would you, it's easy to interpret when you have sort of only one other x variable that you're looking at changing over time, but if you have 2 or 3 x variables that could be changing over time to influence your dependent, how do you go about comparing those?
So the question is, how do you interpret this? So what we're focusing on is here the odds ratio, which is a relationship between 2 variables, right? It's gender related to being alcohol dependent or not. And we can adjust for age first started drinking. We can adjust for a whole bunch of other variables as well. And you can still compute the odds ratio and look at it.
So it would be a simultaneous simultaneous adjustment.
Simultaneous adjustment for several variables, like in Linda's example from the NELS, you adjusted for socioeconomic status and gender to look at the ethnicity effect. That works just fine.
Yes.
I just wanted to see if we could go back to slides 31 and 32 again.
So you want me to do 31, Bengt?
It has to do-
Slide 31 and 32.
It has to do with the syntax. So with, you can use the link option to identify generalized linear models.
No.
So the question is, how do we use the link option here to get what we want?
So if you had here analysis estimator equals ML, you get logistic regression. If you say link equals Probit, then you're going to get Probit regression.
So in this slide over here, though, it's doing weighted least squares.
As the default with
doing a
Probit.
Probit regression.
Right.
I'm just trying to make sure I can.
Yeah, and there's no link option with Probit. So if you had the two-way table, Probit, Logit, Probit, Logit, you know, for weighted least squares, the Logit cell is empty.
So if you, so the question is about what estimator you get, and in this case it's Probit coupled with weighted least squares. You could get Probit coupled with ML if you say link equals Probit over there. The output will tell you which link you get and which estimator you get, the output summary, so you will never have to be confused about that.
So there's, how many different link functions are there then?
There's only, the link option works only for maximum likelihood with categorical outcomes.
Okay, this
It
one.
has two settings, Probit, Logit. Logit's the default, and you can
I
ask
think maybe it's
for Probit.
generalized linear.
No.
Yeah.
Okay, thank you.
Yeah.
So it's not, that link function doesn't lead you to all the generalized linear, but instead we have the designation of the dependent variable as, say, count instead of categorical to move on to more generalized situations.
Okay, thank you.
Yeah.
So